All right, let's get started, everyone. It is 2:40 and it is April 17th. So I hope everybody enjoyed having Monday off class. I had a nice conversation at Microsoft. It's interesting. All these companies do different things with compilers. For example, Google does a lot with compilers. And for example, like in Chrome, they have like their JavaScript compiler and interpreter that they work on. You've seen when I do code demos, I still use Emacs, but the VS Code team is pretty intense with all of the stuff they're doing with parsing and compilers and stuff like that. So it's really cool to see what these companies are doing. There was, I would say about 10 years ago, in the compilers domain, people kind of stopped caring about parsers as much. They kind of said, well, we have tools to parse, we might as well use them and maybe not spend so much time on them. But when I talk to folks at Google and at Microsoft, all of a sudden parsing is coming back because VS Code does so much in terms of syntax highlighting and trying to tell you where issues are in your code. And a lot of that, they roll their own parsers. And so, it's interesting the way that trends come up and down, and especially in compilers. But I do think parsing is coming back in a big way to help make productivity tools. So it's pretty fun for me. I'm also happy to see that there's power. That was very annoying and very disruptive. So fingers crossed that we have power, not just for today, but for the rest of the quarter. We will see. Yep. Was I teaching a class? No, luckily I wasn't. If that happened, I would try to whiteboard it. We'd see how far that would go. My handwriting is atrocious, though, so I'd be happy that didn't happen. Yeah, so I'm glad to see you guys all here and that you all survived. So what are we doing today? We're starting on the next module. We're starting on parsing. So what we're going to do is we're going to do a brief introduction to parsing. We're going to talk about how we actually specify our grammars, specify our parsers, and we do that with what are called production rules. And then we're going to talk about how to use our production rules in derivations and parse trees. And then if we have time, we're going to make it to a simple expression grammar. But our little picture up here shows a piece of source code going to a tree. And trees are going to become very important in this module. So you'll see that starting up. So announcements, like I mentioned, starting module 2. I will say that the material tends to get a little bit more complex. Because of that, I'm not saying that it's difficult. In fact, sometimes I think that complex material is a little bit more rewarding. I would say, what you might have to do is review some of the slides. That's why we post them. I post readings. The readings follow the lectures somewhat closely, and they give different perspectives and some different examples. So I would just kind of be prepared for that coming up here. We do a lot of recursion. I know sometimes people aren't as comfortable with recursion, but here's a good chance to kind of practice that. So that's coming up. Homework 1, it was due on Thursday, but because we had to cancel on Monday, we need to make it through enough of the lecture material for you to get started. So homework 1 is due on Friday. I'll get Canvas updated at some point. And then homework 2 will be released on Friday. At this point, you have plenty of office hours, TA hours, tutor hours left to get help. Just keep in mind that there's no help guaranteed after 5 p.m. and especially on Fridays. So, if you do wait that long to do the homework, just know that the help kind of ends at that point. So please plan around that. Any questions on what we have coming up? Okay, a few clarifications on the homework. These are kind of were also asked in Piazza, but these are some of the interesting ones that I pulled out for this lecture. We talked about HNUM. It says a hexadecimal number. It's like in C, it starts with 0x, followed by digits, which can include A through F. And we said that the character should be case insensitive. Now, what's interesting about this is I think if you were just writing C code, and if you wanted to write a hexadecimal number, you could probably look at this and you could probably think about what it is. But now that we're writing a compiler, we need to think about all the corner cases. And somebody thought of a good corner case, and they said, what about this 0x? Is this x also case insensitive? And so let's say that all characters are case insensitive here. Does anybody know what it is in C? I actually don't know either, but we could go try out. But it just shows, these are the little corner cases that you might not think about too much when you're using a language, but when you're writing a compiler, and even the very first step of a compiler, we start to run into questions like this. Another clarification that needs to be made is for part 4 with the named group scanner. You should not write that regular expression out yourself. You should not make a giant regular expression that encodes your tokens. Instead, you should make this regular expression from those token definitions that you get. And the part of the reason for here is how we're going to grade. So what we're going to do is we're going to grab your tokens, and then we're going to plug your tokens into our own scanner to make sure that your token definitions are correct. And then we're going to put our own tokens into your start of string scanner and your named group scanner. So essentially, your named group scanner does need to derive that regex. It needs to be able to handle that for tokens, for whatever tokens. What you don't need to do is you don't need to order the tokens. We talked about the kind of the prefixes and how that can make things more difficult. You can assume that your tokens are given to you in a good order. Yep.
Is this it's currently graded on the Gradescope, or is it not expected on the Gradescope?
It's enough of this is in Gradescope that if we're going to run into issues, we'll probably catch them. There. Yep.
I know that at the beginning it said not to modify any files that we weren't explicitly told to. Does that include EM scanning?
Yeah, don't. Well, I mean, it actually doesn't matter for EM scanner, right? Because do you have to submit EM scanner? Okay. Yeah, don't modify EM scanner then. Probably best not to. I can't immediately see how it will break, but one good way how to always prove yourself wrong is to tell 150 students to go try things. So yeah, let's say not to modify EM scanner. You can modify it yourself if you want and play around with it, but when you submit it, keep it the same. Yep. Max? You can do what? Good. Okay, so we're going to try to stick to C syntax as close as we can. So when we have questions like that, let's try to go to C and see what it says. And in some cases, we'll have to diverge, but we'll try to be aware of those cases. Yep.
For the hex number, for the 0x, if you made it case insensitive, I found that it sort of broke the test cases.
Okay.
The autograder, I think a lot of people found that was if you don't, if you 0x, the x has to be lowercase. If you check for that, then it passes all the tests. But if you check for also 0 capital X, then it would mess up half the tests.
So if you make it insensitive, it messes up the tests?
Yeah,
specifically the x. Specifically, if the x was case insensitive, then like half the tests would fail for parts 2 and 3.
Interesting. Can you make a Piazza post? Because we should look into that. You did?
Yeah.
Okay. I'll check it out. Yep.
Okay, on that topic, I'm pretty sure it's because like there are like test cases that are supposed to screw you up by having the capital X.
I see.
They're supposed to, I think the autograder is like, that should be an ID, but instead you're parsing it as a hexadecimal.
Okay.
So,
Great. Well, thanks for letting us know. Like we said, this Gradescope is new. So previously, you didn't really get the tests. So the fact that we're giving the tests kind of early hopefully is helpful to you, but it also means that occasionally we have things that we need to fix in them. And hopefully you can also see that compilers are difficult, even at the beginning stages. A couple of TAs and a professor sometimes don't get everything right the first time either. So yeah, we'll work on it. Thanks for that. Okay. Anything else? Okay, and I know I'm going to jump onto Piazza. I've been a little bit sparse the last couple of days, but I'm back, and I'll have a look at it tomorrow, and I have office hours tomorrow. Okay, so let's go over the quiz then to sort of remind us where we're at. So we remember last time we finished up scanners. So let's talk about token actions. That was one of the last things we talked about. Which of the following use cases are token actions not very good for? So are token actions good for changing the value of a token? Yeah, we kind of saw that. We saw that with you can change a cat into a dog if you want. That's very easy to do with a token action. What about changing the token type? Yeah, we saw the token type. Let's see if I have it on the slides. I don't have it on the slides, but actually it's right here. The token type is how we did keywords. We basically made keywords, and we said, you could have int, float, if, and the token action allowed us to sort of check a generic ID and maybe change the token type to a keyword type if we match that value. So yeah, token actions are pretty good for that. What about splitting a token or a lexeme into multiple tokens? Are token actions good for that? Seen some no's? Yep.
Well, the API that we've been following so far specifies that it should give the next token. So if you made a token action that's split into multiple tokens, you might get, instead of the next token, you might get the next two tokens, the next two tokens. So that's like that.
Yeah, exactly. So the API we've been looking at is really just give me the next token, and we're going to see why that is going into parsers. So you could imagine a world where you could split a token into multiple tokens, or a lexeme into, multiple lexemes. But it would break our API, and our API is like this for a reason, and we're going to see that soon. So so you could imagine breaking the API and doing it, but currently, this is not what token actions are good for. What about keeping track of statistics? Like, what if you wanted to count the number of IDs you've seen? Are token actions good for this? Yeah, I would say you would need some sort of scanner state to track it. But if you wanted to count whatever, here we have line numbers. But line numbers is just counting a specific time you see a certain token. You could easily count the number of IDs. You could count the number of numbers you see. You could even track the numbers you see. Yeah, token actions are pretty good at that. So the answer to this is if we want to keep the API that we have, which is going to be important, then token actions are not good for splitting a token into multiple tokens. Okay, which of the following language features make scanner implementations easier? Do regular expression matchers make life easier? Yes, in fact, from everything we've learned, they're basically critical. If we had another quarter to do this class, we could actually talk about how we could do our own, but at this point, they are critical. What about higher order functions? Do they make things nice? Yeah? Okay. Yes, they do. And that was our token actions that we just talked about. We can do token actions that basically refine tokens, and they especially help out with keywords and stuff like that. Now, we're writing our stuff in Python. Python kind of famously doesn't have types, but you'll probably notice in some of the code we provide you, we try to do the type hints in Python. Do types make things easier for this? Who says yes? Who says no? Some people say no. Do types make things in general easier for people? Yeah, so generally people, and we're going to see this more and more as the class progresses, just to kind of keep the different types straight of what things return, what things take in, especially because we're going to be doing a lot of recursion. We wanted to talk about, if it takes in a node and if it returns a node and stuff like that. I do think types, in this case, help keep your head screwed on straight. We can, some of it's a matter of opinion, but I do think they help out. And maybe in a few more homeworks you might agree, and if you disagree, that's all right too. What about interpreted languages? Does that make things easier? I mean, we're using Python. Python is an interpreted language. Does anybody have thoughts? Well, yep. Yeah, and we will be getting to the point where we need to debug more and more and more, and interpreted languages tend to have really good debugging features. I'd say this one's kind of a wash. Let's see. So we said interpreted language. It's nice where we're at. We know how to use Python's debugger. Python, can help us catch lots of errors like out of bounds memory accesses and stuff like that. But there's also other languages that are compiled that end up being people really like to write compilers in, like OCaml that can be compiled. People tend to really like that language. Yep.
Technically, OCaml is also interpreted.
Yeah, they have an interpreter.
Run that mode.
Mm-hmm.
Yeah, that's just mostly to say it doesn't really matter.
Yeah.
You get writing compiler in JavaScript will really suck, versus writing in OCaml will be very easy.
Yes, exactly. So there's different cases, to be made for each. So I'd say this one doesn't really matter. Just make sure that you have a good regular expression matcher. Make sure you have higher order functions. Types help out quite a bit, so you probably want them. So just kind of make sure you have those, and then whatever language, whatever language you like, you can use. The next question is, we talked a little bit about scanner generators, like we saw Lex. Really kind of what we're implementing is really kind of a scanner generator where you give it tokens and then it gets token. So, is this true or false? That scanner generators have the same interface, which makes them very easy to switch from one to another, like if you're using Lex or if you're using the name group scanner that you're writing. Is this true? Is it false? Yeah, we saw this a little bit last time. And this is one of the questions where there's some truth to it and some false, so you could really go either way. You can assume that all scanner generators take in regular expressions. That's a pretty well agreed upon interface. And most of the time, they give you the nice operators. They give you the nice digits, plus, question mark, all the nice things that sort of make our life a bit easier so we don't just have to use the base regular expressions. All of them probably provide token actions, but they're probably going to be expressed differently. And you can assume that all of them have a function similar to token that returns the next lexeme. And like we said earlier, that's an API, and we are going to stick to it because it is going to be useful coming up. But in Ply, it's token. In our scanners, it's token. In Lex, it's called YYLex for some reason. But yeah, essentially, you need to have a function that returns the next lexeme in your stream. And you should also know that these exist. Right now, we're writing our own to get some experience. But if in 5 years, when you have to write your own compiler, you should reach for something like probably not Lex. It's a bit old these days, but maybe something like Antler. That tends to be a newer compiler framework, or I know Rust has some really good ones too. Okay, so as one final one, we can go over a little bit of it. If you were given a scanner, and if you knew that it was either an exact match scanner, a start a string scanner, or a name group scanner, and you could give it any token definitions that you wanted, are there experiments that you could do to determine which one it actually is? Who thinks yes? Okay. Who has an experiment? Does anybody have a token that they could differentiate exact match scanner and SOS scanner? Yep.
I was thinking not for exact match.
Okay. So which ones were you thinking about differentiating?
Name group and any of the others.
Okay. Yeah. How would you do name group and any of the others?
If you were able to specify the order, you could do have plus first and then plus second.
Mm-hmm.
If it matches plus, it's probably the name group.
It takes the first choice it can, right? It's pretty lazy. It will grab the first thing and return it. Yep. So if you have a token for plus, if you have a token for plus plus, and if you feed it into the scanner in that order so that it sees plus before it sees plus plus, name group will match the shorter one. We don't want that. And so that's an experiment you could do to figure out what implementation your scanner was behind the scenes. Anybody else have any thoughts? Yep. That's exactly right. So you could have one token to go back to plus and plus plus. If you had one token and, let's see, if you did something like, let's call this one P plus, and if we had let's see, plus or plus plus, something like this. Exact match scanner will give you the longest one because it starts at the end and it tries to match the longest thing it can. Start a string scanner is going to give you this first one because that's the semantics of the regular expression match. So you can do it with a single token to differentiate between these two. For the name group scanner, you can use 2 tokens. Okay, any questions on that? Okay, so, yep.
If you just did the example with the plus plus and the single plus, wouldn't you still be able to differentiate between all 3 of them?
Let's see, could you differentiate between all 3 of them?
Like if you ordered it so that the shortest one was first, you would get plus for NG scanner. Wouldn't you get both for SOS scanner, and then you would just get the longest for EM scanner?
Okay, so you're saying if you had one token, right?
Sorry,
2
2 tokens.
tokens.
You got a plus and an increment.
A plus and an increment. So Okay, so you had like plus equals plus, incur equals plus plus, right? Yes. So remember with the, so this is kind of the one that we said differentiates named group, right? When you do start of string scanner, remember the start of string scanner is going to match both of them and take the longest one. So, named group and exact match should both give you that one. If you want to differentiate exact match and start a string, you need to put them as in the same token. Yep. So tricky. Yep. And some of you probably have or will run into that bug when you are implementing your scanner. Yep. So you do have to, in that start a string, you do have to search and find the longest match. Yep. Okay. Good questions. Anyone else? Okay, let's start parsing, new stuff. So parsing, just a note on terminology, is sometimes when people talk about parsing, sometimes they group scanning into it as well. Technically, they are different, but a lot of times when you're on forums or just talking to other developers, parsing kind of considers all of it. Even more specific terminology, what we're going to be doing here is called syntactic analysis. And if we go back and if we revisit our view of the compiler, remember we have our input program, we have our front end. Our front end basically handles parsing. And parsing creates structure. And once we have enough structure, we can move to the optimizations, which sort of loop and do the optimizations. And then we can go to the back end, and finally we get machine code. With parsing, we're still living up here in the front end. We need to create more structure before we can move on to the optimizations. And in fact, in doing parsing, we can actually identify kind of more errors at this point, and the sooner we identify errors, the better. If we go to our sort of bigger view that kind of needs to take a detour on the slides, remember, our input program is a string. Here, if you have a simple kind of physics equation where position equals initial plus rate times 60, the first thing we did is we tokenized it. We know how to do this now. That creates a token stream, or a lexeme stream, which is an ID, a sign, ID, binary op, ID, binary op. We break it down into its parts. And now for the syntax tree, which is basically where we're going now, we're going to take this stream and we're going to put it into a tree that looks like this, where nodes are operators and then our leafs are going to be tokens or lexemes. So this is where we want to eventually get to, is this tree. So, like we mentioned, lexical analysis turns a string into a stream of tokens. Syntactic analysis determines if those tokens fit into the syntactic structure of the language. And if we go and if we revisit our natural language example, the one that we were sort of looking at a while before, we said the dog ran across the park. We know now how to break this into, article, noun, verb, preposition, article, noun. And if we wanted to say what some valid sentences are, we might start to organize those tokens. And we might want to say, if you're trying to describe a natural language, well, you can say article, noun, verb, preposition, article, noun, just like we have up here. Maybe you can say article, adjective, noun, verb. And now we're starting to describe what is called the grammar. We're ordering these tokens and saying which order of tokens end up being syntactically valid. So if we kind of just took this idea and if we wanted to expand it, and even thinking ahead of how we're going to put it into a programming language, if we just specify our grammar as a list of tokens, is this good enough? Can we define a language like C by just saying, it's an ID, a sign, variable plus variable? If we just sort of started designing our language like that, is that going to work? Well, it's simple. You can say, variable equals this, but it's probably too simple. Programming languages are a little bit more expressive than this. Maybe, rather than having, one sequence of tokens, maybe we get a bunch of sequences of tokens. Maybe we say we can match this, or we can match this, or we can match this, or we can match this. And these are all just lists and sequences of tokens that are describing our language. Is this getting us closer? Is this what we want, or are we missing something here still? Yep.
I think we're saying if we wanted parentheses, you can be able
Yeah, so parentheses are a big thing. It's really hard to imagine how to do parentheses here. But maybe I could, maybe I could just say like ID, assign, lpar, ID, rpar. I can come up with a sequence that has some parentheses. Right, exactly. So I can come up with specific cases. What you're saying is that there's a structure, and we want to be able to encode that structure here, right? So yeah, I can come up with some cases for us, but it feels a little bit wrong, right? We want to do something a little bit more systematic. And yeah, potentially, the problem with this approach is, while it might work for English sentences, for programming language expressions, there's potentially infinite of them. Like if you're writing a programming language, you could say x equals 1. You could say x equals 1 plus 1, 1 plus 1 plus 1 plus 1. Your programming language isn't really going to give you a limit on how long that can be. I mean, of course, you will run into limits with how much hard drive space and memory you have, but we don't want to actually explicitly enumerate these out. But we have a weapon. We have a weapon in our belt that we can use. We talked about regular expressions. Maybe we could use regular expressions here. Maybe we could say, like in English, we could say article, adjective. We can have a bunch of adjectives, right? We could just put an adjective star here. Say like, the big red car, whatever. But you could just have as many adjectives as you want. And we know how to use regular expressions. We know that we have tools for matching them. Do we want to use regular expressions to specify our grammar, like regular expressions over tokens? Well, they seem to work pretty good last time. Maybe we could try it out. So let's think about what could go wrong. So if we have these tokens, let's say we have like numbers, and let's say we have plus and multiplication, could we describe a simple grammar just using regular expressions over these tokens for mathematical expressions? Like what's a very so first off, what is an expression? Think of, well, does anybody want to say? It looks like you might want to say, Cameron.
Like in general, or?
Sure, yeah, an expression in general.
It's I guess like some combination of like words that form some idea.
Okay, I like it, and I like being general because we are in kind of a very general compiler setting. We'll go a little bit more specific, and let's say a math expression is something. Yeah.
I'm trying to think of the right word, but I want to say it's a collection of symbols. What do symbols have meaning?
Yes, I like the way everybody's thinking because it's a very compiler way to think in terms of symbols and evaluating symbols. Yes, so we'll take it to math just for now, and then we'll go more abstract in a bit. An expression evaluates to something is what I would say. An expression always returns something. So like if you have 1 plus 1, you can evaluate that. That returns 2. If you have just the number 5, 5 evaluates to 5. So kind of any combination of numbers and arithmetic operations, that can be evaluated. That's an expression. So for example, in a language like C, if you have x equals 1 plus 1, x equals 1 plus 1, this whole thing, maybe there is a way to view it in the way that whole thing is evaluated, but not really. It's updating some variable. But the 1 plus 1, that is evaluated because that returns a value. And if you have like 1 plus y, that is also considered an expression because once you know the value of y, that can be evaluated as well. So an expression is really kind of what happens on the right-hand side of an assignment. It needs to be evaluated, and it's typically of what we think about as like a mathematical sentence. James?
If you were to think of like a regular expression for like expressions, you could do something like number concatenated with operator, and then parentheses, clean star, and then number. Maybe.
Wait, so am I doing it right? Num, op.
Num op, and then around num op.
Yep.
Sorry, yeah, like brackets or.
Yes. Okay. Num op and clean star here.
Yeah, and then at the end of that, num concatenated.
Num.
And you would have like
Yeah. So that's exactly where I was going with this. If we want to describe expressions, I think James hit it right on the head. The simplest expression we can have is a num, but then additionally, like before that num, we can have like 1 plus or like 5 times. So we can basically describe expressions as a regular expression over our tokens. So that seems pretty good. And what we can do is we can think about it a little bit more. So I kind of have the same thing as you, James, except I put the num at the beginning, and then I have plus or multiplication here instead of 1. And so, so basically what you had, just a little bit mirror version. So if we want to try it out on some expressions to see if we can match those expressions, if we have this regular expression, does it match 5? Yeah, because we just, cleany star can make it not repeat any of this. So 5 is just a number. Does it match 5 plus 6? It's because we have a number, then we instantiate this once, we pick the plus, and 6 instantiates that. What about 5 plus 6 times 3? Yeah, so this 5 gets the first number. This plus 6 is one instantiation of this suffix, and then times 3 is another instantiation of that suffix. So this feels pretty good. It feels like we can kind of use regular expressions to, hopefully reduce that infinite amount of possibilities issue that we were running in before. But, and this is kind of a place where it might feel like we need to just kind of take a step forward in our abstractions. And when we start parsing, we need to start thinking about creating structure. And when we create structure, we want to encode meaning. And when we look at something like this, like 5 plus 6 times 3, when we want to evaluate this, what does it actually mean? Well, what it means is that we need to do 6 times 3 first. Why do we do 6 times 3 first? Yep. Yes, exactly. Order of operation, something we learn way back. And then we do whatever the result of that is 5 plus 6. What if we switched it like that? We do this first one first. When we start doing, when we start having these regular expressions, it really doesn't give us the ability to think about the meaning. It just sort of matches. And this worked for the scanning. Scanning was like, I'm just going to match any tokens, and I'm going to give them tokens and pass it along. We want to start getting meaning here. And one thing that ends up being very difficult is if we want to have parentheses. Parentheses are very important, again, because of order of operation. Maybe we want to do the add first, and so we need to put parentheses in there. And so if we need to put parentheses in there, we need to add tokens for those parentheses, an open parentheses and a close parentheses. And then what we could do is we could take James's regular expression, and you could start to kind of add parentheses to them. And you start to get a little bit like alphabet soup up here, but what you say is like, maybe we could have an open parenthesis at the beginning, so open parenthesis question mark. You could also potentially open a parenthesis there, and maybe you can close a parenthesis after the number. We're not going to go over it too much because this regular expression is getting a little unwieldy, but what you would find is you could start matching things like this. That's totally fine. You could get that far. But you could also start matching things like this. Like when we say there's an optional open parenthesis there, we're never saying like, hey, you also have to close your parenthesis. So at this point in the compiler, we actually want to get to the place where we can say, if you open a parenthesis, you have to close it. We'd consider that a syntax error. That's why Visual Studio can underline that in red, because we want to be able to catch that issue as early as possible. And this is the part in the compiler where we want to start to encode that kind of stuff. So while regular expressions are a powerful tool, we know a lot about them, but at this point, we might just need to kind of throw our hands up and say, we need something new. We need something new to express these more complicated grammars. So, and if you take 103, what you're going to find is there's a very classic theorem that basically says regular expressions cannot match an open parenthesis to a closed one in the general case. That's just not within its capabilities, no matter how hard you try. We did see the HTML example on Stack Overflow. So what we're going to do is we're going to work our way up the Chomsky hierarchy. And we're going to use what is called a context-free grammar. So who here has used a context-free grammar? A few people. OK, so probably less than regular expressions. So let's talk about what a context-free grammar is. And I'm going to play the same annoying trick that I did with regular expressions. So given a language L, a string S is either part of that language or not. We talked about this with regular expressions. For example, integers are the languages of, it has 5, 6, -7. Integers do not have ABC probably. And languages are grouped into families depending on how hard it is to determine if a string is part of that language. So in our tokens, we were playing with sort of the simplest language, which is a regular language. This is a Chomsky hierarchy. We can go up to a family of languages that is slightly harder to match than regular expressions, and that's context-free. So we're going to be living here for the next little bit. Chomsky, he has several other levels to the hierarchy that you can learn about in 103 or in a linguistics class. We don't really use these in compilers. They tend to be just very difficult to both specify and to match. So it's nice that we can live down here in the context-free world. OK. So again, like I said, I'm going to do the annoying trick I did for regular expression. So how do you define a context-free language? A context-free language is a language that can be recognized by a context-free grammar. And why is this annoying? Because now we have to define what a context-free grammar is. So let's look, much like regular expressions, with regular expressions, we said, here's like a character, and we can put a star there, we can put a union there, we can concatenate it. Let's actually look at some of the syntax of how we specify a context-free grammar. And in this class, we're going to use what's called Bacchus-Noir form, or it's also often called BNF. A lot of tools use this. If you end up going and looking at like a C specification and stuff like that, a lot of times they'll use this. Occasionally, I'll deviate from the exact syntax, but I think it's pretty clear what we're referring to. The way you specify a grammar is that you have non-terminals. So think about a non-terminal like a variable in your program. You can have as many of them as you want, and you can basically name them whatever you want. And each non-terminal maps to one or more production rules. And one of our non-terminal symbols is designated as the start. Sometimes it's called the goal symbol. So looking over here, the way we specify it is we have our non-terminal. So this is just one of our non-terminals. Like I said, variable name, you can name it anything. You can have as many as you want. Then you sort of do some sort of delimitation. Here I have : equals. And this non-terminal can map to a production rule. So we're going to talk about what a production rule is in a second. But the same non-terminal can map to several production rules. And we typically specify that with this OR operator. And it behaves very similar to the OR operator in regular expressions. So basically you say, this non-terminal maps to this production rule or this one. And then I have a non-terminal over here that maps to this production rule or this one. Yep?
So this would be like going through all your tokens and you find, let's say, a number and then a plus. Then you would go and match it and say, oh, I need to pass an infix expression.
You'd start to specify, yeah, and we're going to talk about that in a second. We use our tokens in our production rules. Yes, but right now, if you just use your tokens in these production rules, you'd basically just be back to regular expressions, right? Because right now, the only operator we've talked about is OR. And so the real power of context-free grammars is coming up. Yes. Any other questions? OK. Leading almost exactly into that. So production rules contain either a sequence. They contain a sequence that consists of either other non-terminals or terminals. And in compilers, our terminals are typically tokens. Occasionally, just for the slides, we might see, kind of literals being used in there. Considered, this is pretty easy. You could just say plus would be you could specify plus as a token, but sometimes we'll just write it in there. So, for example, if you wanted to have a non-terminal that said, hey, I want an add expression, then I could say an add expression equals a num plus num. Not too bad. A multiplication expression is a num times a num. Maybe you want something that multiplies two add expressions together. Then you could say a joint expression is an add expression times an add expression. And this add expression needs to be specified like it is up here. And maybe you want something that handles addition and multiplication expressions. So you could say, this expression over here is a num plus a num, or a num times a num. So this probably feels kind of just like we had before, like regular expressions, except now we kind of have variables that allow us to modularize our code a little bit better. But the real power of context-free grammars comes from recursion. And what can happen is a production rule can reference itself. And so this is a silly example. It's given in the book. But for example, if you wanted to say have some grammar for whatever a sheep says, a sheep could say ba, followed by other things a sheep says, or it could just be normal ba. So what we can do is to show that a string belongs to this grammar G, we have to provide a derivation. And when we provide a derivation, there's a few ways to do it. But to begin with, we're going to do a table method. And so in this table method, what you do is you start with your start symbol. And your start symbol, in this case, we only have one symbol. It's sheep noise. But your start symbol will always be specified. And then what you do is you pick one of the rules and you expand it out. And you keep track of something called a sentential form. So let me show you. So here's our very silly language. It's just one non-terminal with two production rules. And if we wanted to try to match the string ba to this, what we do is we make a table. So we always have a starting place. And that starting place, we have our starting symbol here. Now, what we do is we pick a production rule. We say, right here we have sheep noise. In sheep noise, we can either go 1, which gives us this, or we go 2, which gives us this. Well, we are trying to match this simple string up here. We're just trying to match ba. So if we want to match that, we just pick rule 2. And then if we pick rule 2, sheep noise turns into ba. And then our sentential form matches the string that we're trying to match. So this one was pretty easy. Let's try matching ba, ba. So we're going to start. We have our starting non-terminal here. If we want to do that one, in this case, we need to pick rule 1. So if we pick rule 1, sheep noise turns into ba, followed by sheep noise. And then, if we pick rule 2, we turn sheep noise here into ba. So we get. And you can think of these things as just concatenating with each other. And you can think of us having an ignore white space rule. So at this point, we've now derived this. So hopefully you can see. James?
What if you had sheep noise twice? Would you have to make 2 tables or something? Or would they follow the same? Can you have one follow rule 1, one follow rule 2, rule 2?
So that's a good question. And I think you're thinking ahead to kind of an algorithm that we can do, right? Because at some point, if we have 2 sheep noises, we need to make a decision on which one we expand. So at this point in the lecture, I want us to think of this as sort of a paper and pencil thing that we as humans are thinking about. And in fact, we're going to do an example in just a second, too. And eventually, we're going to talk about how to turn this into an algorithm to actually help us parse. Good question, though. Anyone else? OK. So let's talk a little bit more about mathematical expressions and maybe some of this. Actually, I'm going to go over here. Maybe our new tool, context-free grammars, can actually help us solve this a little bit. So if these are our tokens, numbers, and let's give us plus equals plus and molt equals molt. Let's give us those. Could we give ourselves a simple expression language? So let's actually, maybe instead of deriving it, we can just go look at it, and we can kind of see how nicely these context-free grammars allow us to incorporate matching parentheses. So remember, our secret weapon here is recursion. We start off with an expression. And just like anytime we do recursion, I'm not very good at it, so I like to start with the base case. So the simplest thing an expression can be is a number, right? So that's one of the production options for an expression. Another thing an expression could be is an expression op num. I mean, we could put that as an expression as well. This kind of follows the regular expression we had earlier that we saw, where an expression when you have an expression, you can always add a +5 or times 6 or whatever at the end. The other thing, though, that you can do is you can have an expression and you can put parentheses around it. Now, this is powerful because every time you have an open parenthesis, you have to match it with a closed one. And this specification of the grammar will ensure that you have matching parentheses. And we did this only with a couple of lines of specification. And this is part of the power of recursion and what it gives us. Here I also have op specified as plus and times. You could also do that in tokens. Yep.
But this wouldn't deal with operator precedence, though. So
Nope. We have. I think we'll get there next lecture because there's a lot to bake in here. So yes, this is not the end of the story, not by any means, but it is getting us closer. Baby steps. Yep.
Does this match like 3 times 4 plus 5 in parentheses?
It should. Let's see.
Is the only thing that can be on the right side of an operation with a number?
Let's see. You might be right. I think this one was given in the book, so let's go through and let's try to match this one, and then we can try to repair it, because occasionally these things don't handle all possible cases, especially when we're doing illustrations. but yes. So let's do an example here. And this one's just slightly longer. So we're going to do a start. We're going to have an expression. That's our top one. And we want to match the string a plus b times c. So what rule should we pick first? And again, this is kind of a human in the loop experience, at least for now. Yep. Rule 1. Is that what we should do? Let's see. So if we do rule 1, then we're going to expand this to, let's see, x per. Is that right? What do people think? I'm seeing. Yep. Yeah, so it's always a bit tricky to know which one. What I worry about here is if we do rule 1, we have a parenthesis at the end, and there's not a parenthesis at the end of this string. So, and there's no way how to kind of get anything after this parenthesis. There's no non-terminal that we can expand there. So, in fact, we have to do rule 2 here. Yes. So then we get x per op id. Okay, so we could do something like that. What rule do we apply next? Anybody have any thoughts? Okay, let's rule 1. Okay, so we could do rule 1. That would give us open parenthesis x per close parenthesis op id. Okay, so this is you're right. so good job. And the other thing is, though, is there something interesting about that choice? Was that the only rule we could have applied here if we saw this? Was there another choice we could have made? And this is kind of getting to James's comment. Yep. Yeah, we could have also applied, let's see, we're doing a times, we could have applied 5, and we could have turned this into a multiplication there. So there's a couple choices that we could have done at that point. Doesn't matter which one we choose. Interesting. We will be answering that question in depth over the next lecture or so. anyways, we could continue to expand that out. And, like I said, this is kind of a human in the loop process. We're not talking really about an algorithm to do this, but rather you as a human picking the rules and imagining that you are able to get this down to this form, which matches this string. Now, like we said before, before we get there, one important concept that we're going to see over and over again is, in addition to a table, we can also visualize this derivation as a tree. And how do we do that? Well, we start off with all our non-terminals are our nodes. So expression, we're going to start off with a non-terminal at the top. And then whatever we expand this expression into, we expand this expression into an expression op ID. That's going to be expanded into an expression op ID. And then op is going to get expanded into a multiplication there. So that goes down to multiplication there. This expression, we apply rule 1 to get parentheses on either side. So that goes down like that. And we keep going, and we keep going, and we keep going. So we can get a tree. This is what's called a parse tree. So what's really nice about parse trees is I really think that you can really just say this expression expands to these components. And what you can also do in a parse tree is, we have this tree here. If you want to get the original string back, all what you need to do is you just need to do a post-order traversal. You go down this leg, you go down there, there's parenthesis, open parenthesis, you come down here, go down to expression, you get A plus B, close parenthesis, times C. So you can just traverse that tree, and you can get your string back. So these trees are going to be increasingly important. So like we said before, when we kind of came up with this derivation, we made some choices. We said, there wasn't really any choice here. There was one thing to expand, so we expanded it like this. But then in this example in the slides, what I did is I expanded the op first, and then after the op, I expanded the expression, and then we got to this point, and then I expanded the op here, and then we expanded the expression there. Does anybody see any pattern that I chose to do here? Yep. Yes, exactly. So every time we had a choice, basically we started at the end of the sentential form, and anytime we ran into a non-terminal, that's what we expanded. We said, here's the ID, that's a terminal, but here's a non-terminal, I'm going to expand that. And then here again, when we had a choice down here, we went, right to left. So we started with the op, we expanded that, and then we finally expanded the expression. Now, what you could have done is you could have gone the other direction. Here, we apply rule 2 at the beginning, but then instead of applying rule 5, we apply rule 1, and that's because we're expanding left to right. So here we go expression, and then we get expression op that, and we just choose the non-terminal from left to right that we want to expand. So we call this one a right derivation. We call this one a left derivation. Okay? So, yep.
So you know, is ID the base case?
Yeah, ID is just going to match one of these A, B, or C. So it's one of our tokens. You could imagine a world where you then expanded this out to I guess that would be C. Yeah. But yeah, we're in this case we are saying IDs are our token. Yep.
After the input code, will that ID basically be a tuple after you expand it?
Yeah, because it'll be a lexeme. We'll get its value, and we'll either get its value or we'll have the ability to look up its value in a simple table. Yep. Okay. Now again, this is going to be something that comes back in a couple of lectures, but when we draw the tree, regardless if we did the left derivation or the right derivation, we get the same parse tree. And that's going to be important coming up. But the parse trees, depending on whether you can get the same or different parse trees, depending on your derivation, is going to be important. So just to kind of give a little bit of a look ahead of where this is going, if you can get different parse trees, you have what is called an ambiguous grammar. So we know the word ambiguous. We know, like, when somebody says something that's ambiguous, it means that it's not clear what it means. Maybe it could mean a couple of different things. And so we get the same things that show up in programming languages of whether it's ambiguous or not. If it's not ambiguous, it just means one thing, and everybody can figure out what that one thing is. But if you can have different parse trees, then potentially it can mean different things. So this is sort of a classic example, and again, this is in the textbook, and you can read about it a little bit more if you want. But if you have a statement, a conditional statement, you might try to specify it this way. You might basically try to say if expression, and I'm just going to imagine that we have expression defined someplace else. But so if we have an expression, remember expression returns something, so expression can be like if true, if false, expression can be 1 or 1, whatever sort of Boolean expression you have. And then we have the keyword then, we have statement. So, if this expression is true, then do this statement, else do a different statement. That's kind of your if-else case. But a lot of times when you have conditionals, you also just have an if. You might just want to say if that expression is true, then do that statement. And otherwise, you might just have other types of statements in your program, like an assignment statement or something like that. And if you look at this string that we have, you say if expression 1, then if expression 2, then assignment 1, otherwise assignment 2, would we be able to derive this? Kind of seems like it, right? Like this is just an if-else statement, and this is just an if, right? And maybe some of you saw it a bit differently than me, though. Yep.
Yeah, you just have to disambiguate it and say which way the else would go, because it's most likely that the else would go to the inner if. And then you would probably want to add parsing so you can get an expression with brackets around it.
Yes. Brackets would basically help this out completely. And it's probably why, and there's a question in your quiz about it, why a lot of us use brackets even when we don't have to, because otherwise things get very confusing. Because you might, in your mind, you might parse this as you have if, you might parse it as, you have this if-else statement, and then you have this if that essentially leads into that. Or you can say you have this is just an if statement, and then this is if matched with that else. You need to know, essentially, does this else match this if, or does this else match this if? And you can get two different parse trees depending on sort of which one you think. So, whichever one you thought, given this grammar, whichever one you thought, there's a parse tree for it. And like we've said before, at this stage in the compilation, we want to start encoding meaning. It's a parser is a little bit more advanced than the lexer, than the scanner. Meaning, these two different parse trees mean two different things. What this one says over here is it says that inner else matches this if. This if and else is at the same level in the tree, so this is your if else. This parse tree says that the outer if matches the else. And, we don't want our programming language grammars to be like this, because when you write something like this, even if it is confusing, when you compile it, it should do the same thing from one compiler to another compiler, regardless of how they get their parse trees. So this is what's called an ambiguous grammar, and we're going to see a bunch of cases on how those come up, and we're going to talk about a bunch of cases on a bunch of ways how to fix them, and you will get a bunch of experience in your next homework doing that. So that's essentially what I said. We talked about the post-order traversal. So that's essentially what we want to talk about today, because we're going to do a lot more, like I said, with ambiguous grammars next time. But I want to close out today with kind of what I think to be an interesting example. we talked about a context-free grammar, and so far we were kind of talking about using them to specify our programming language. But the other thing you can do with them is you can, if you have a context-free grammar, you can generate random strings that belong to your language. So for example, if we go up here to our, let's see, if we go to this, this example, basically you could say, you could have like a random chooser, and you could say, oh, choose this one, and then randomly pick one of your production actions, and basically just randomly pick production actions until you end up, with a string at the end. So you could basically generate random strings that are part of this language. Now, what we do is because this is essentially how C is specified, what this means is you can essentially generate random C programs. And there's this really cool line of work. It's called C-Smith. Was started at University of Utah roughly around the time I was there. But they took the formal grammar of C, and they basically said, we're going to test compilers to see if compilers are correct. Turns out compilers, just like all other software, can have bugs. And so what they did is they generated random C programs, and then they if it's a random program, you don't know what it's supposed to do. But in the end, it doesn't really matter what it's supposed to do because it's supposed to do the same thing for any compiler. So they generated a random program, and then they compiled it with different compiler flags, different compilers, and then they run it, and then they check the outcome. And if you see a program doing something different here than a program doing something different there, then you don't know what the bug is, but you know that there's probably a bug. And so when they did this, they found over 400 compiler bugs. These days, Google has a couple of servers that just run this 24/7, testing their compilers, because it actually ends up, as soon as you have that grammar, it ends up being pretty easy to generate random C programs. And the big challenge here is how to avoid undefined behavior, because if you're generating random programs, maybe you are using an uninitialized variable. So there is a bit of magic here. It's not magic, but you essentially have to be a little bit careful to avoid things like uninitialized variables, divide by 0, stuff like that. But it's kind of interesting, like if you were to really generate a random program, it can be kind of interesting to see what they look like. And so, for example, I generated a couple of them before class, and let's see. So like what you can see is you get stuff that looks like this, because it's all just random. It's all just randomly pick if is an array access, randomly pick numbers, randomly pick whatever you want. And you end up getting programs that look like this. But the cool thing is that this is still a valid program. Like what I can do is, I need to remember what to include, but I can compile this with GCC. These are warnings, they're not errors. But, 305 warnings. And, I have no idea what those all are. But I can run it, and I can get some sort of outcome that sort of has tracked the computation going through there. And so that's what this research has done, is they basically generated these crazy programs and then just compiled it with different compilers, and like I could if I compiled this with -03, oops, thank you. I would get all the warnings again, but but then what I could do is I could just run it again, and I could check that checksum, and this is a very good way to find compiler bugs, and it's, like I said, it's been really impactful for the way that people actually test these sorts of things. So I'd run it. We can't see it because it's buried in the warnings, but that would be the same thing. So if you wonder why compilers tend to be correct, even though they're incredibly complex, testing methods like this is one way how people have really made them robust. Okay, it is 3:45, so let's call it good for today. More ambiguous grammars next time. So thanks, everyone.